Yesterday, I discussed the fundamentals of avalanche photodiodes. What I want to discuss today are the gain bandwidth product of an avalanche photodiode. I want to discuss noise factors and also some typical structures of avalanche photodiodes. Avalanche photodiodes, as I mentioned, work at slightly higher reverse bias voltages, so they result in gain. You can get multiplication of carriers, and due to the random nature of this multiplication, one has excess noise. Yesterday, what I discussed was the breakdown condition, and we had come to the condition that for alpha n is equal to alpha p, simplified case is equal to alpha, the breakdown condition was alpha dx over the width is equal to 1. Now, alpha itself is a function of the electric field. Okay? So you cannot take alpha out unless if you have a diode with the electric field is constant. Okay? This is a typical PIN structure. Okay? This is also called a Reed diode because it was proposed by Reed a long time back. In this case, over this region, electric field is constant, and therefore alpha is constant, so you can take alpha. Then the condition becomes that alpha W is equal to 1. Okay? Only if you have a constant electric field. In general, you do not have a constant electric field, so you have to calculate this breakdown condition numerically. Now, as I said, the diode is actually biased slightly less than at the breakdown voltage, and we know from considerations of a PN junction that for a one-sided abrupt junction, VB is E maximum W by 2, and this is equal to epsilon S EM squared by twice Q NB. Okay? This is a junction like this. Suppose it's a P plus N junction, okay? Then NB is the carrier concentration in the lightly doped region. And for a linearly graded junction, this is standard PN junction theory. We have the breakdown voltage is twice EM W by 3, which is 4 EM 3 by 2 twice epsilon S by Q to the power half. And A to the power minus half, where A is the grading coefficient. So this is for a junction in which you have this is for a junction where you have the okay, say this is acceptors, this is donors. Okay. Whereas for this junction, linearly graded junction, we have okay, acceptors, this is donors. Okay. This is an abrupt junction, and this is a linearly graded junction. Okay, and A is the slope of this grading. Okay, this is standard PN junction theory for calculating the breakdown voltages. Now, if we carry on where I left off last time, the avalanche gain in general, where alpha n is not equal to alpha p, is just m is equal to one minus 0 to w alpha n exponential minus 0 to x. This is what I derived last time. Okay, now this is the general expression. Now, if you have position independent ionization coefficients, that means the electric field is constant as a function of x, alpha n and alpha p. So constant electric field. Okay, so then you can take these out of the integrals, and then you will get the condition that m is equal to 1 minus alpha p by alpha n exponential alpha p and alpha n are different, but they're constant over the width of the diode. 1 minus alpha p by alpha n exponential okay, the expressions are similar, but here this is 1 minus alpha into the whole thing, and here it's 1 minus this into the whole thing. Okay, so now we can put the special condition. This is the general condition for a reed diode of the multiplication factor. Now, if we put alpha n is equal to alpha p is equal to alpha, then of course we get simple condition. Okay, alpha p equal to alpha n. So this is 1. This is 1. Okay, this is 1 minus 1, 0, so e to the power 0 is 1, okay, e to the power 0 is 1, so this is simplified, and you get m is just equal to 1 minus alpha w, okay. And as I've shown, the breakdown occurs at alpha w is equal to 1. So we don't go to the condition alpha w equal to 1. We keep alpha w to be slightly less than 1, so we can control this gain. And this alpha itself, w is constant, so this alpha itself is controlled by controlling the voltage, applied voltage. Okay. We have a condition that, say, if m tends to infinity, and under this condition, the gain bandwidth is equal to 3 by 2 pi tau average, where tau average is just the Tn plus Tp over 2, where these are the transit times, where Tn is W by Vn, electron transit time through the width W, and Tp is W by Vp is the whole transit time. So this expression is slightly approximate because we've taken m is equal to infinity, but so obviously we can increase the gain bandwidth if we can reduce W, okay, and Vn and Vp are properties of the material. So if you have higher saturation velocity, obviously then this gain bandwidth will increase. Okay, now let's get to the topic of noise. There is avalanche multiplication noise. Why? Because this is a random process. We don't know when an electron is going to collide and create extra electron hole pairs. Similarly, hole, when it picks up enough energy, can create electron hole pairs. So there is defined an excess noise factor called Fm, which is mean square over square of the mean. Okay. And this excess noise factor Fm is obviously a function of alpha n and alpha p. The excess noise factor was derived by McIntyre in 1966. This is a seminal paper on noise and APDs, and this still stands. And in this, he shows that for electron injection, F is equal to Km plus 2 minus 1 by m 1 minus k, whereas for hole injection it will be F is equal to k dashed m plus 2 minus 1 by m 1 minus k dashed, where obviously k and k dashed will depend upon k is alpha p by alpha n, and k dashed is just the reverse, alpha n by alpha p. So k is 1 by k dashed, but for simplicity it's written this way. So you see that the two cases differ. Why? Because alpha n and alpha p are not the same. Obviously the effective masses also come in and they play a role, and m also comes in. Okay, so we can, depending upon the material, depending upon k or k dash, we can choose either electron injection or hole injection. Now let's take special cases for these. Suppose we take that special case where, just for simplicity, alpha n is equal to alpha p. This is not a very, very realistic case. Okay, then k and k dashed, k equal to k dashed is equal to 1. Okay, and then what do you get? That in this relation, this is 1. So this goes. Okay, this. So F is equal to m. Okay, F equal to m. Okay, so if the multiplication factor is large, 10, 20, 100, okay, so this is large. This excess noise factor is large. However, suppose we take the other case, that the, say, optimum case, in which, say, alpha p is much less than alpha n. Okay, so k tends to 0. Okay, so if you look at this, k tends to 0, this term goes, okay, this is 1, okay, so this tends to 2 minus 1 by m, right? So F tends to 2 minus 1 by m. and it tends to 2 if m is large. Okay, if m is large. Okay. So in this case, it is desirable for electron injection. Obviously, it will be for electron injection. Okay, for electron injection, it is desirable to have this, that k tends to 0. Okay, for hole injection, it would be preferable to have k dashed equal to 0. Okay, and notice that f is equal to 2, which is constant, independent of m. This is much better than f equal to m. Say m is 10, 20, 100. Okay, so this is excess noise factor is quite large. Here the excess factor is only 2. Okay, it's constant. So this is much better than the case where alpha p is equal to alpha n is equal to alpha. Okay, so that's why right at the beginning I said that when we looked at those figures of alpha against 1 by e, it is better to have, say if that is alpha, it is better to have, and this remember is a log scale. Okay, so if alpha n is much larger than alpha p, okay, sometimes of course remember I've said beta and alpha. Okay, but now this is clearer, I think, to talk about alpha n and alpha p. So if this is it's like this, then it's a good material. Okay, but on the other hand, if you have some material in which alpha n and alpha p are very close together, okay, so that would be the other condition. Okay, so this is in a nutshell the desirability of having a material with low noise. I'll come back later on to show how recent band structure engineering can artificially change this. Okay, this so far as I've shown, this depends upon the material. Okay, it just depends upon you choose a material which has a large difference. Silicon is good. Okay, this germanium is not so good. Silicon is like this. Germanium is rather like that. So silicon is a good material. But can you enhance this artificially using either strain layers or quantum wells, or so that I'll discuss later on. Let's give an example of some typical. This is a classical example of a germanium APDs were designed fairly long time back. The structure is a little special over PIN diodes because we have the same sort of thing. We have the active layer is N, say N plus. This is the lightly doped P layer. Okay, and okay, this is a this is effectively the I region. This is the junction. Okay, so if you have a very sharp junction here, the electric field tends to be large. So we want to say this is the back contact. We want to have what we do is we have a lightly doped, this is a guard ring. Okay, so the electric field at this region corner is spread out over a larger region, so this electric field does not become too high, breakdown does not occur at this corner. Okay, it's like a lightning rod. Why is a lightning rod good for arresting lightning? Because it's very sharp, the curvature is very high, so breakdown field is very high. So this is trying to reduce the curvature and have reduced the breakdown field. Okay, and the rest of it is just if you have a dielectric, okay, say SiO2 passivation, and then you have some metal contact. And because it works at high field, the material itself here has to be very pure, very high quality, without any dislocations, edge bit densities, so that there should not be breakdown. You should not have a little microplasma breakdown between between here and here, okay, or across. Okay. Now, for this germanium APD, what I want to show is how the gain or the multiplication affects noise and signal. Okay, suppose this is, we can change the value of multiplication from 1 to say 50 by applying voltage, okay, changing the voltage. So this is say 10. How does the output signal, this is say minus 65 dBm. dBm means in milliwatts. Okay, 1 dBm is 1 milliwatt. This is minus 110 dBm, so this is very weak signal. Okay, so as the multiplication factor is increased by applying voltage, the signal goes something like this, okay, proportional to m squared. Whereas there is a background of receiver noise, various sources of noise. So this receiver noise is always there, independent of the device. Now, as you increase m, the noise, the avalanche multiplication noise goes up, something like that. Okay. So this, say for a bandwidth of 1 megahertz, this is the avalanche noise, and this is the signal. Okay. And so, what do you find? That since this is going as m cubed, okay, this slope is larger than this slope. So, higher signal to noise ratio is obtained at under this condition, right? Because if you compare what is the noise is going like that, okay? Noise is constant here, signal is increasing, okay? Signal to noise ratio. So you're looking at the difference between this line and this line. And the maximum difference is here, because thereafter this noise is increasing as m cubed and this is going as, okay? So this shows that there is an optimum value of multiplication factor which gives the highest signal to noise ratio. So for example, we can show that for m less than 30, signal power goes as m squared, noise goes as m cubed. So highest signal to noise ratio is obtained at m is equal to 10, where it is 40 dB, S by n. Signal to noise ratio power, 10 dB means 10, 20 dB means 100, 30 dB means 1000, 40 dB means 10 to the power 4. So 10 to the power 4 gain you are getting through this. Okay, the question is, okay, what is the bias? How does a bias change the properties? We'll look at that. In the meantime, let me just show you some. Okay, can you see this? Okay. Okay. As far as as far as it goes, these are different types of avalanche photodiodes. This is the one that I've shown you. Okay, this is N plus P, P plus. Well, I've drawn this yourself. This is the same as the one that I've shown. Okay, broadly, you don't have to look at the D. This is just a N plus N, P, P plus. Okay. Here you have a basic things are that you have guard rings, okay, to reduce the chance of breakdown. Here, if you look at the geometry, this is a Mesa type, okay, N plus N, P, P plus. Okay. This is beveled. Why is that? Because then the breakdown field is reduced, okay. And here you have sideways illuminated, like in the PIN diode, sideways P plus and N plus. Okay, so these are the standard structures.
If you take N region half circle, then
what do you mean?
we are reducing radius of curvature.
Yeah, this N plus region, but it's difficult to make the whole region curve. So what we are doing is just this region. Okay. It can be done by diffusion or nowadays by ion implantation. Okay, you just ion implant in this area and diffuse. Okay, and as a result, remember if you just look at this, if you think of an abrupt junction, okay, VB is 1 by NB. Okay, so if NB is very high, okay, like that N plus layer, then VB is going to be small. Okay, so what we are doing is that at that junction we are having NB low. Okay, so we are increasing breakdown voltage. Right. So what here, if in addition to the curvature, this N plus region is highly doped, so breakdown voltage will be low. Okay, and it will be especially low here. So we are trying to, this is low of NB, so obviously breakdown voltage will increase. Okay, a typical structures, okay, I can draw some structures, for example. Oh boy. One can have, in order to optimize the gain bandwidth product, one has, okay, this is just a doping concentration, okay, ND or NA. Okay. This is a P plus pi P pi N plus structure. Okay. Then one can have a structure. So where is the junction? The junction is obviously, junction is here. Okay. One can have an N plus P pi P plus, okay, structure. So here the junction is here. Okay. And if you just, okay, it's interesting to analyze what is the, this is X, okay, X. What is the electric field profile? Because remember, the electric field profile determines where the avalanche takes place. Okay, so where is, this is the junction. Okay, so the high field will be in that region. The electric field profile is the highly doped region. Say this is P plus. Okay, this is P plus pi P pi N plus structure. Okay, there's no field here. The field builds up to this region. Okay, and this is a very narrow structure. Okay, and it builds up here. So you have a constant electric field in that region. Okay. Here, of course, the structure is different. Here, the electric field is maximum. So electric field in this N plus region, the electric field is it suddenly builds up. Okay, and it's maximum here. It remains constant. So by tailoring the field profile here, the avalanche multiplication will occur only over, or perhaps over just this region, where the electric field is very high. Here, the whole region, you get avalanche multiplication. Okay. So if you reduce the avalanche multiplication distance, then sometimes the avalanche delay is reduced. I hope you can see this, right? Okay, so if you plot the the 3 dB bandwidth as a function of m, then one gets diagrams like this. As for different values of alpha n, alpha p, alpha n by alpha p, okay, going from 1 to 5, 10, 200, okay, 10 to the power 4. And you find that for m is equal to alpha n by alpha p, then you get a variation something like this, where the bandwidth, this is almost constant independent of gain. And this is for the special case of electron injection. Okay. So alpha n, for electron injection, alpha n, k should be small, so alpha p should be small compared with alpha n. And MW, the gain into the frequency, it turns out is W by Vn. This is the transit time due to electrons into alpha p by alpha n, which is a small quantity. Okay, so this is a small quantity, this is a small quantity, so the whole thing is so this is a general expression for this condition when m is equal to alpha n by alpha p. Okay, so m is equal to alpha n by alpha p. This is this gain term, okay, and this is the transit time term. Okay, so for large gain bandwidth, what do we want? We want W should be small, Vn should be large, and obviously this alpha p by alpha n should be small. Okay. And remember, this also gives you low noise. Okay. So these are the main conditions for good performance of a avalanche photodiode. Let's go directly into the current multiplication at high light levels. maximum DC multiplication is limited by series resistance and space charge limited effects. Okay, but if you neglect that, then MPH, M photocurrent, is equal to I minus MD over IP minus ID, where I is the total multiplied current, IMD is the multiplied dark current. Okay, because even without light, little current, dark current is there, that is also multiplied. Okay, IP is the total unmultiplied current, and ID is the unmultiplied dark current. So, for high intensity, what do we have? That IP is much larger than ID. Okay, this can be neglected, and of course we can say that the IR drop is much less than the breakdown voltage. Suppose we have VR is the actual reverse bias applied, VB is the breakdown, then MPH maximum. From this expression, what we are doing is this is negligible, this is negligible. Okay, so we just I by IP and this can be written as 1 minus VR minus IR over VB to the power n. VR the reverse bias tending to VB. Okay. Suppose we neglect this IR, and if VR is equal to VB, this is 1. Okay, then MPH becomes infinity. Okay, so we keep this slightly VR slightly less than VB. Okay, so we can get the correct gain, and this is equal to typically NIR by VB, one approximation. Where what is N? N is an index, breakdown index, which could be something like the value of 2 for a particular. So, what is MPH max then? MPH max, just from that, is approximately equal to VB by N IPR. And if in the dark, when IP is less than ID, then we have MPH max VB, that's the breakdown voltage. Okay, so higher the breakdown voltage, the better it is. Lower the photocurrent, or low, if this condition obtains, then you replace IP by ID into series resistance. Okay, so we can, that is as far as the maximum multiplication factor is concerned. Similarly, we can draw a graph of how excess noise factor, that FM, varies as M, and we find that it obviously a limiting condition when K is alpha P by alpha N. Okay, when this is equal to 0, then we have this excess noise factor is just 2, right? That is the original case. Now, for different when this is when K is equal to 0, okay, and for different values of K increasing 0.01, okay. For F proportional to M, one gets, and then for F proportional to M squared, okay, so this 50. So this just shows that given this value of alpha P and alpha by alpha N, which depends upon the material, okay, we can choose the value of M, which will give us the desirable noise, that we won't have too much noise, and this obviously is valid only for electron injection. So the two graphs enable you to calculate the noise factor as well as the gain bandwidth for different devices. I may just mention that, okay, how can you increase the just a pictorial representation of noise. Okay. Why is it better that if you have a single carrier which is creating noise, okay, which is avalanching, what happens? You have, say, an electron which is going from, let's see, an electron is going from here. This is sample 0 to W, okay, and at points here it creates an electron hole pair, okay, and so what happens? The holes start going the opposite direction. Okay. Suppose there's another event here, the holes will, okay, and the electrons are multiplying, and okay, whereas the electron is proceeding. The electrons are multiplying, okay. The holes are multiplying, but they are not avalanching. Okay. So the number of electrons is going up, say from 1 to 2 to 4 to 8, etc., etc. And the holes are going up 1 to 2 to 4. Okay. Now suppose you have the other case in which this is the case where alpha P is much less than alpha N. Suppose we have the case where alpha P and alpha N are both appreciable, then what happens? Then you have an electron trajectory there, okay, and the holes are multiplying, okay. Electrons are creating electron hole pairs, but then suddenly a hole here, okay, a hole here will cause multiplication, okay. So as a result, what will happen? The electron hole pairs will branch out, okay, and here again multiplication will occur, okay. So holes start multiplying there, okay. So this is the case where alpha P and alpha N are both appreciable. So there is more statistical noise because there is avalanche multiplication going on in this path as well as this path, and then so this is much more a random process, and therefore this is where you have less noise, FM about 2, and this is more noise, Fm proportional equal to m.
Sir, here why a hole motion is perpendicular to electron motion?
This is just
You can
representation. Okay, this is distance. Okay, and this is time. Okay, this is distance and time. Okay, this is distance and this is sort of time.